here are neurons where we're just taking, we take an electrode and we suck onto the electrode and pop a hole into it. This is a technique called patch clamp. This is what my lab does. And then you can actually, through that same electrode, inject current and simultaneously measure the voltage from that cell. And that current will make the neuron fire. So you can see as we increase the amount of current, you start seeing the cell spiking. And here is another cell where you start with low current and it really occasionally fires. So this is the kind of thing that you see in a realistic noisy neuron. These little bumps here are probably synaptic inputs coming from other cells. And occasionally, both the current here and a synaptic input causes the cell to fire. And you inject a little bit more current, and now this starts firing. And the highest firing rate is much faster. Whereas this one, you can see, starts off fast and then slows down. This one here somehow likes to spike in trains. Spikes a couple times and then stops, and then spikes a couple times and then stops. And that's called a chattering cell. Somebody from an old lab that I worked in was the one who discovered chattering cells. The intrinsically bursting, so these guys like to fire a bunch of times. Often this is your action potential goes up and actually causes a lot of things to happen up in the dendrite and then comes back down and reactivates the cell. Calcium can be responsible for that. We can go in and remove calcium and sometimes see things like this bursting go away, and it turns it into more of a regular spiking. So we categorize cells. One of the reasons why we have bursting cells is that a cell fires an action potential. The release probability of a neurotransmitter is not that high. But if you keep spiking several times in a row, you dramatically increase the release probability on the subsequent spikes. And so you can actually dramatically increase the reliability of the response in the postsynaptic cell by sending multiple spikes in a row. And that's why you'll get different cells. The cell morphology is also really important. So here is actually the exact same computer model of each chamber, same sodium, potassium. These are some form of Hodgkin-Huxley equations. But now they're just changing the shape and how all these chambers are connected. So if a very small, compact cell like this likes to fire very periodically, whereas a guy that looks like has a big tuft up here and a lot of basal dendrites, when it fires, you actually get signals that go back up into the axon and then come back down and then trigger the next spike, and it turns it into a spiky neuron just by the fact that it has a different shape. So shape and behavior are not completely independent of each other in neurons. This is a really fascinating cell. This cell, you put in a little bit of current, so this cell is not firing at all. You put in a little current, fires a bunch of times, and then you turn off that current, and that neuron just starts spontaneously spiking. Pop, 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 pop. And then you put in another stimulus, and then it starts firing faster. Pop, 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 pop. And then you put in another stimulus, and it starts firing even faster. So the same current here, here, and here is exactly the same, but you can see the cell keeps firing faster and faster after each input. So it is integrating the inputs. It's a really fascinating cell. How this actually works, it isn't really well known. One of the guys who works on this is Mike Hasselmo, Hasselmo is named the son of Niels Hasselmo and is at BU. The guy who actually discovered this, I think I mentioned a couple lectures ago, there was that guy who died of herpes zoster that I knew of, a very painful death. He was the guy who discovered this and died of herpes zoster a couple years later. Very tragic.